All right, so this video is about chapter 8, which is about energy and equilibrium. I wrote KEQ on there, but don't worry about that. So this is like one of my favorite chapters of chemistry. It also has to do a lot with biology as well as kind of where they start to come together a little. And so I'm so excited to teach it to you guys. So let's go ahead and get started. So we already talked about endothermic and exothermic reactions. And so we're going to dig a little bit deeper into that as well. But first, I want to introduce the idea of spontaneous processes and non-spontaneous processes. So I have this little picture here. So non-spontaneous processes is like this little guy pushing the rock up the hill. It takes some work. It can't happen on its own. So you have to put energy in for a non-spontaneous process or reaction to happen. So another example that I like to think about is sledding. So if you want to go down the hill, right, you have to climb up it. In turn, when you're sledding down that hill, you're not doing much, right? Energy out. This process happens on its own. Granted, there's a little push, right? The same with this little man pushing the rock off. There's a little push, a little bit of energy, but once that rock gets going, it's going, right? So this happens on its own. And it releases work. You might be like, what do you mean? How does it release work? Well, when you push that rock down, it starts to build momentum, starts to build speed, starts to cause friction with the ground below it, right? That friction causes heat. Heat is energy, right? That kinetic motion and speed, maybe you have a target at the end of the hill and it pushes that target over, right? You didn't push that target over. The rock did, going at a certain speed. And so this spontaneous process, this process that could happen on its own, released work and therefore energy. And so we're going to start to see these graphs, these energy diagrams, where it shows a reaction progress. I'm going to abbreviate reaction RXN on the x-axis. So basically it's saying here's the start of the reaction, here's the end of the reaction, and then the y-axis here is energy. So at the start of the reaction, the reactants were at a low level of energy. The reaction took place, and the products were at a higher level of energy than when they started. Now, this is a little deceiving. You might think, oh, if you're at a low energy and then a high energy state, oh, it seems like you've gained energy. It's misleading. So we went from here to here positively, positive on the x-axis. This corresponds with energy in. So at the end of the reaction, we were left with something of a higher energy than when we were to start with. Whereas on B here, it's the same scale, right? This is the start of the reaction to the end of the reaction. And this is my energy. I started here with my reactants. My reaction took place, and I ended at a lower energy level. So starting here and ending here, I went down on the y-axis. And this corresponds with energy out. So it's a little misleading, but if you look at these graphs as a sledding hill, it helps. So maybe I had to climb up the hill a little. I got to the top and whee! I landed all the way down here, right? That's awesome. That was a big hill. I went a lot on my own. Whereas, let's say on the left side here, if I was sledding and I walked myself all the way up here, and then I sled down this hill, and I ended here, I'd kind of be like, well, that wasn't great. I mean, it was fun, but I worked a lot to get up here to only end here. That's kind of how I think about it when I look at these graphs. So we'll see these graphs a little bit more here in a second. But I want to introduce the idea of entropy. So entropy is the measure of disorder. So when we're looking at this picture here, all these little particles, they're well ordered, they're nice and neat. This is low entropy. I spelled that wrong. Whereas, let's say after a reaction, all of these particles, they're very disordered. And this corresponds with high entropy. So entropy is this kind of complex topic, but I just wanted to apply it to solid liquid gas for the purposes of this course. So looking at our states of matter, solid has very well-ordered particles, and so it has low entropy. Liquid starts to get a little bit less ordered, and it has a little bit higher entropy. I'll put medium entropy. Whereas gas is super disordered and has super high entropy. So this entropy, right, it's disorder. And it really, when you think of the example of gas, and the gas particles are boom, 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 they're pouncing all over each other, right? They gain energy by bouncing off of one another. And so high entropy is favored. even though it's disordered, right? And we usually don't think of disorder being favorable. Disorder in the universe is favored because the reactions can get energy off of each other, basically. So when the gas molecules are all over the place, boom, 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 just being free little gas particles, they are bouncing off the walls, basically, and feeding off of each other's energy. So kind of think about like a classroom with crazy kids all on like a sugar high, right? They just feed off of each other's energy and just get even crazier. That's how I like to think about it. So we're starting to put together a bunch of terminology for the endothermic and endergonic and spontaneous reactions and all that jazz. Basically, let's organize it. So we talked about energy being put into a reaction. We talked about energy being energy in and energy out, right? So energy in was when energy was absorbed by the reaction, right? So that's that snowmobile, I'm not sorry, snowmobile, the sledding hill where you climbed the really steep side and you ended up going down the shallow side and you're kind of were disappointed. You're like, well, why did I hike up that far, right? The same principle goes for endothermic reactions and endo ender sorry not endo endergonic reactions, right? These all require energy in. We have that positive energy on the x-axis or the y-axis of our energy diagrams. Okay, and this is associated with a non-spontaneous reaction. This is not going to happen on its own. So all these terms all mean energy in, right? Energy is being absorbed by the reaction. It's endothermic, it's endergonic. It has that positive value of energy on the x or the y-axis. It's non-spontaneous. Where energy out means all of the following. Energy is released in whatever form, heat. So if it's released in heat, we call it an exothermic reaction. Sometimes we also call it an exergonic. I always say this word wrong and spell it wrong. Exergonic. It's associated with the negative energy on the y-axis of the energy diagram, right? So this is when you started to climb that hill, that sledding hill, and then you got to the top and you're like, oh man, this is great. We get to go down the other side and like, this is a huge hill. Like, this was great. I didn't have to put in that much work to get to the top of this hill, and I'm going to go down really far, right? So these are all spontaneous. They will happen on their own, right? Once you get going down that hill, you're going to start to gain speed without even trying. So I want to define reaction rates. It's not that we ever have to calculate this on any of our owls or our homework, or I'm sorry, on the exam, but I just want to bring up this idea is that reaction rate is the change of speed, or I'm sorry, the change in concentration over time for the reaction, right? So if we had some initial value of, let's say, 5 molar concentration and we ended 3 molar concentration, and this happened over 30 seconds, right? We could do the math and calculate our rate. Don't think too hard about the math on this one. What we really care about is that our reaction rate is the change in concentration over time. So what you do need to know for the exam, though, is how can we change these reaction rates? Well, we could increase or decrease the concentration, and that will affect the reaction rate. Let's start this slide. So talking about reaction rates, right? Can we speed up a reaction or could we slow it down? And the answer is yes, right? We have these 4 different factors that influence reaction rates positively and negatively. So the first is concentration. We could increase the concentration or decrease the concentration. And that could change our reaction rate. We could change the state of matter of our reactant, the nature of our reactions, right? We could put it in a gas phase, a liquid phase, a solid phase. You know, if I'm going to do some kind of reaction with a gas, like we talked about, that's favorable. The universe likes gases. And so that's probably going to speed up if we were to use, let's say, hydrogen gas over liquid version of hydrogen. That's probably going to speed up our reaction. Temperature. If we increase temperature, our reaction rate is going to increase. If we decrease decrease temperature, it's going to decrease. In the presence of a catalyst. So what the heck is a catalyst? A catalyst is an enzyme. It's going to speed up our reaction. And how it's going to do this, and I'll talk about this in a second, is it's going to lower the activation energy, but it's not going to change the change in energy. So you're probably like, wow, that's a lot of words. Can you please explain that? Yes. So looking back at these energy diagrams, right? Here we have a spontaneous reaction. We start here and end here, right? We start lower. That sledding hill, that little hike we took really paid off. So in all of these energy reaction diagrams, we have this little hump. No matter where we end, if we end here or up here, we have this hump. And this hump is called the activation energy. And so the activation energy is that little push that it takes to get the reaction going, right? So even if we're sledding down this big hill, sometimes there's still a little push, a little barrier to get it going. So we can quantify the change in energy. We can put numbers on it. And so that's the difference from the starting point to the end point. Right? The activation energy is not accounted for in that change of energy. When we talk about the energy difference, we're talking about solely where did we start and where did we end. And so bringing this all to the idea of an enzyme or a catalyst is the presence of a catalyst is going to lower the activation energy. It's going to make this hump lower, but it's not going to change where the reaction starts and stops. So I like to think of a catalyst as like, again, sliding down that hill. Now, let's say I'm a 10-year-old kid. I'm going sledding. I have my mom and my dad with me, and I have my 5-year-old brother. I can ask my 5-year-old brother to be the one who pushes me to get me going, sledding down that hill. Okay. I might not start at as fast as a speed, and I might not gain as much momentum as if I were to ask my mom or my dad, who's a full-grown adult and can really give me a good push. I like to think about that as being an enzyme or a catalyst, is asking your mom or dad to push you down the hill, right? They can get you going a lot sooner than your baby brother can. So let's look at your OWL question 9, which is deciphering these energy diagrams. So here we're shown the energy diagram of a reaction. 2O2 yields O3 plus O. And so we're starting here and ending here. So when we think about our start to our end, we went up, we went positive on the x-axis. And so we know all of this is synonymous with being an endothermic reaction, an endergonic reaction, that this is non-spontaneous, this is not going to happen on its own, and that we must have taken energy in to do this reaction. So all those terms are synonymous. So when you see, one of these, an endothermic or energy in, you can start thinking about all those other terms because they all are lumped together as one big party, basically. So here it's asking us to define the reaction. We could define it lots of different ways, but specifically they're like, is it energy in or energy out? Is it endothermic or exothermic? Well, because we know that we ended at a higher place than we started, we know that it's, like I said, synonymous with all those other terms, and that it's endothermic. So now it's asking us to look at the values here. And so it shows us the value from the very start to the very top here of that hump. And it shows us the value of our start to our end. So like I said, the value of our start to our end is the change in energy. So we can go ahead and just plug that in there. But our activation energy is that little bit of energy it takes to get to the hump and get over the hump. So here in this specific diagram, it doesn't give us a direct activation energy, but we can solve for it by subtracting the 411 from the 392. And so that ends up being 19. So even if this were to be a exothermic reaction, you could still solve for the activation energy the same way. So let's go ahead and look at another problem. So this specific problem is going to be similar to your OWL question 10. And it's talking about collision theory and reaction rates. So this one's a little tricky. So it's asking us to select all that apply. So first, I'm just going to look at my energy diagram and just start to decipher some stuff here. So I'm starting here and ending here. So I'm going down. So this is a spontaneous reaction. I know this is also synonymous with being exothermic and exergonic. And that energy must be taken in these kind of reactions. I'm sorry, energy released. So energy out or energy released in these kind of reactions. So I've gathered my thoughts here. Here they're directly giving me the delta E, and they're directly giving me the activation energy. I don't have to do any math for it. All right, so according to collision theory reaction rates, which of the following are true? So collision theory, I summarized with how do we change the reaction rates, and I talked about the gas particles. So in the presence of a catalyst, the value of energy difference between the products and reactants will be larger than negative 70 kilodaltons. So this is not true because the presence of a catalyst changes the activation energy and not the difference in products and reactant energy. So we can rule this answer out. Increasing the concentration of the reactants, basically C2H4 HCl, would increase the rate of the reaction. And I'm going to apologize. I don't know if I actually said this in the previous slide, but concentration and reaction rates have a direct relationship. So increasing the concentration will increase the reaction rate. Decreasing the concentration will decrease the reaction rate. So this statement is true. The third statement, increasing concentration would have no effect on the reaction rate. This is not true. We know that changing the concentration in any form, up or down, will change the reaction rate. The fourth statement, raising the temperature would increase the reaction rate by increasing the number of successful collisions. And this is true. Increasing temperature and reaction rates, again, have a direct relationship, just like concentration. If we increase the temperature, we will increase the reaction rate. The fifth line, at a higher temperature, the rate of the reaction will increase because the value energy difference between the products and the reactants will be smaller than 70K or negative 70 kilodaltons. So while the first half of that is true, a higher temperature will increase the reaction rate. The second half is not true. Increasing the reaction rate is not going to change the difference in energy between the products and reactants. It's whether we increase how fast this reaction happens, we will never change that number. So next we're going to talk about chemical equilibrium. So in reactions, I had been previously drawing them with a forward arrow only, where we have products and reactants and nothing else. This is not necessarily true in the universe. Sometimes reactions can go forward and backwards. So each of these would have a different rate. I do want to say that reactants are going to be whatever's on the butt of the arrow, and products are always at what's at the arrowhead itself. So the forward reaction is the one in which the arrow is going this way. The reactants for the forward reaction are going to be H2I2, and the products for the forward reaction are going to be HI. If the problem were to state something like in the reverse reaction or the backwards reaction, what are the reactants and what are the products? Then we'd be looking at the butt of the arrow where the reactants are HI and the arrowhead would be the products. But most of the time we're talking about, when we're asking about identifying products and reactants, we're just talking about one forward reaction with one forward-facing arrowhead. So each of these reactions, the forward and the backwards, have different rates. They can be happening at different rates. So chemical equilibrium is when the forward reaction becomes equal with the reverse reaction. So the rate of the forward and the rate of the reverse become equal. And so this is depicted here in this graph on the left, where, maybe this is the backwards reaction and it's happening kind of slowly, but building speed. And the forward reaction is happening really fast, but is slowly decreasing speed. And over time, they end up at the same speed. Now, I want to reiterate that this doesn't necessarily mean that the concentrations are the same, just that the reaction rate is the same. And so here's a graph depicting chemical equilibrium, but showing concentration on the y-axis. And so maybe, again, this pink being the backwards reaction, we end up at a really high concentration of HI, where the forward reaction slowly decreases concentration. But at some point, they both level off. And this is equilibrium. So So the rate of the forward and the backwards equal each other. So rate forward equals the rate backwards. So along came this guy named Le Chatelier. It's French, Le Chatelier. I think I'm pronouncing that correctly. And he came up with this principle, Le Chatelier's principle. So when a system is in equilibrium and then a change occurs, it changes in concentration, temperature, volume, pressure, the system will adapt to maintain a new equilibrium. So I'll put this, I have two examples here. So of course I have a running example, right? So let's say we have a person running on a flat surface at, let's say, 7 miles per hour, right? They're running on a flat surface. They're obviously putting in some energy, right? But they're in a groove, right? Well, along come some stairs, and we've changed the system, right? And so to maintain that 7 miles per hour, we have to really put in some more energy, right? We have to change up what we're doing. We have to change up what we're doing in order to maintain that 7 miles per hour. And so that's Le Chatelier's principle, is that we're trying to maintain this equilibrium, but sometimes that's not a perfect world. And sometimes certain things come along and push us away, and the system will react in a certain way to maintain it. So here's my other example. I couldn't find a great sunny picture, but this will do. So maybe you're walking along, there's clear skies, so you're dry, right? You don't have anything to worry about. But let's say it starts raining. In order to stay dry, you use an umbrella. You're changing what you did in order to maintain dryness. Right? So this is Le Chatelier's principle, that we're going to react in some way to maintain equilibrium. So I talked about it earlier in the definition of Le Chatelier's principle, but we have these different factors that could affect equilibrium, such as concentration, such as pressure, such as temperature. But the one thing that will not affect equilibrium is a catalyst. Catalyst only affects activation energy. And speed of reaction. Basically, it speeds up the reaction by lowering the activation energy. So you might be wondering, well, if concentration, pressure, and temperature affect equilibrium, how do they affect equilibrium? So my rule of thumb is that an increase in concentration will push away, and this will make sense here in a second. And a decrease in concentration will push towards. Whereas an increase in pressure will push away, and a decrease in pressure will push towards. Temperature is a little bit tricky. This depends on if the reaction is exo or endothermic. And I'll show you an example here in a second. So looking at your question 11. So a system is at equilibrium. So now they've added some bromine, right? They've increased the concentration. These brackets always mean concentration of bromide. So how I like to draw arrows over the reaction. So if we increase this side, we increased the bromide, we have to do something in order to react, right? We have to grab an umbrella, we have to put in some more energy to work up that mountain and maintain 7 miles per hour, right? We have to reestablish equilibrium in some way. So increasing concentration means push away. So if this is where we increased concentration, we're going to push away from it. So in this case, that is moving in the forward reaction. So what does, bromide's partner here, NO, do in response? So bromide is like, whoa, I'm sorry, NO, nitrogen oxide is like, whoa, what are you doing? Why did you just increase? He's like, we can't be moving faster than we just were. I'm going to slow my roll because you're being too loud over there, basically. It's how I like to think of it. You're being too loud. I'm going to quiet down. That happens when you're on the same side of the arrow. Now, if this were to ask for the concentration of NOBR, well, what does NOBR think? He's like, whoa, bromide, why'd you just go nuts? Well, I'm gonna go nuts because our reaction forward and backwards has to be the same. So if you're gonna start yelling, I'm gonna start yelling. And so he would increase. So if they're on opposite sides of the arrow, they're going to react similarly because they're trying to balance each other out. But if they're on the same side of the arrow, such as NO and BR, they're going to act oppositely because they don't want to overwhelm one side of the reaction. Okay. Another example here. Temperature, right? I said this temperature does affect equilibrium, and it depends on if it's an endergonic or exergonic reaction. So they basically have to tell you. So they can tell you by literally labeling it endothermic or exothermic. Here, they've told us, because they've put kcal, which is a form of energy, on the product side. Now, like I said, we're gonna consider this the forward reaction, right? So this is an, I'm sorry, exothermic reaction. So if we were to increase temperature, an exothermic reaction is going to react by pushing away from where the energy is. So if we increase here, he's like gonna push away to this side. I'm sorry, that's not what the question's asking. The question's asking if we were to decrease. Well, there's what's to happen if we were to increase. So if we were to decrease, though, we'd be filling a void, right? We need to go fill that void, and therefore we would push towards. So in this case, this is running in the forward direction. So this question additionally asks us, what's going to happen to this Br over here, this bromide? So we're pushing away, we're pushing in this direction. This bromide is at the butt of this arrowhead. And so he's like, I gotta slow my roll. We're going the other direction. I'm not the key player right now. And so he decreases. And if you remember, when we had our example in the last slide, 2NO plus Br2, 2NOBr, right? We were also pushing in the forward direction and looking at what happened to NO. It was also decreasing when it was at the butt of the arrow, right? Okay. So that's the end of chapter 8. Le Chatelier's principle is a tricky one, but once you get the hang of it, it's almost like it clicks and it just becomes instinctive. Watch some videos. Maybe there's a YouTube video out there that can explain it just a little bit better than I could. Or sometimes hearing it the second time, things start to click. So we will resume with chapter 9 in class.